I present to you the effects of body location and biosignal feedback modality on performance and workload using electromyography in virtual reality. I am Jessica Sehrt, and I am a PhD candidate at the Frankfurt University of Applied Sciences. For understanding and improving muscle control as interaction technique, it is important to consider the physiological difference between muscle tension caused by moving a limb, called isotonic contraction, and isometric contraction, which must be consciously activated without any movements. Isometric contraction is, for instance, desired to prevent artifacts in the signal caused by movements or to prevent crosstalk of multiple neighboring muscles. Particularly, assessing the isometric muscle activity using electromyography sensors is indispensable for a wide range of medical, assistive, and interactive applications. Such systems are desired, for instance, when isotonic muscle movement is not even possible at all due to motor impairments, to control electric wheelchairs, exoskeletons, and remote robotic systems. Such systems are desired to trigger events in hands-free interaction to prevent unintentional motion-based input, or can even support the restoration of neural pathways when only the intention to move a limb is trackable, for instance, after a stroke. The so-called biofeedback-loop describes a system that displays the biosignal back at the user during interactions with the physiological functions of the own body. Closing the biofeedback loop increases body awareness, often causing changes to one's own behavior, thoughts, and even body functions, which are typically not consciously perceived. In particular, closing the biofeedback loop using EMG sensors is helpful where muscle control can support motor functions or information about the muscle activity signal is required to regain such control. Carolus et al. Showed that visual and auditory EMG-based biofeedback can increase body awareness during physical activity. Choi et al. Showed that a closed-loop biofeedback via tactile stimulus based on user's heartbeat rate was effective. And Palermo et al. Presented an augmented reality environment to provide visual feedback of EMG activity to amputees when training for using an EMG hand prosthesis. As not all humans activate and use their muscles in the same way, we hypothesized that there are differences in the user's input performance between different areas of the body. Therefore, we conducted an exploratory VR study with 18 participants and a within-subject design with the independent variable body location. Based on a standardized Fitts law target selection task using EMG and a head-mounted display at the pointing device, as well as subjective assessments, we measured performance and workload. We used the input of the hand at the VR controller as control condition and compared it to the EMG input at the biceps brachii, the muscle of the upper front arm, to the triceps brachii caput laterale, the muscle of the upper back arm, to the gastrocnemius caput medialis, the muscle of the inner calf, to the temporalis anterior, the muscle of the temple, and to the flexor carpi radialis, the most distinguishable muscle of the forearm. Objective performance measures of the study on the left, with the average throughput results from the Fitts law task, between the body locations show the highest throughput by the VR controller, which was to be expected as it was installed as control condition. During experiment execution, we found that the participants were not able to contract the temple muscle isometrically. After exclusion of the temple, the quantitative results on the throughput suggest that stationary isometric muscle contractions do not significantly differ in terms of their input performance between the muscle groups tested. Importantly, there were no interaction effects with the index of difficulty, as shown by the regression slopes on the right, with the target selection time of each body location as a function of the effective index of difficulty. This finding indicates that the participants tend to point equally well during conditions with all body locations independent from the level of difficulty of the task. The workload score of the raw nasal tail X questionnaire and its subscales from the study show regarding the main score that the triceps received a significantly higher workload rating than the muscle of the temple. The VR controller received significantly lower ratings for perceived performance than the triceps and also significantly lower ratings for effort than the biceps, which was to be expected as it was installed as control condition. Importantly, qualitative results revealed that the participants probably did not activate the temple muscle isometrically and instead used isotonic movement, despite our instructions. Comments were temple is only good to control because you can press the jaw to activate the temple muscle, or temple muscle activation needs movement of the eyebrow and forehead if you do not want to involve the pressing of the jaw. EMG biofeedback can help users to focus on their own muscle tension. However, which sensory cues are suitable for rendering EMG signals and closing a biofeedback loop is currently unknown. As humans have a limited set of resources available for mental processes, we hypothesized that task performance based on biofeedback from multiple cues can cause difficulties. Thus, we investigated 3 feedback modalities, which were visual, auditory, and tactile. We conducted a 3-way full factorial within subject design study in VR and with 40 participants. Due to the low variance of the throughput in the first study, its observability during the experiment to ensure isometric contractions, and its relevance in related literature, we used the biceps brachii at the front of the upper arm for EMG input in our second study. The throughput performance measures for each biofeedback modality show that the highest throughput was achieved using visual and tactile feedback, as well as when no feedback was rendered. A main effect for the auditory feedback indicates that the average throughput was significantly lower when auditory cues were present compared to when not. Target selection time as a function of the IDE shows that the target selection time does not depend on auditory, tactile, or visual cues. The results of the raw nasal TLX questionnaire show significant main and interaction effects on the feedback modality. The subjective quantitative results also indicate that input performance can be improved by presenting muscle tension as simultaneous tactile and visual feedback, alongside the objective results. The results also show that there is no single modality that systematically improves the target selection time or workload. Interestingly, while the main effect indicates that audio has a negative impact on throughput, the subjective frustration was lower when audio was on. Participants appreciated informativeness and usability in the biofeedback modalities. Importantly, the results show that some modalities can produce stress due to their obtrusiveness through repetitive patterns, or even by information overload while using too many modalities. Negative side effects were caused by fatigue, exhaustion of the muscle or through the system in general, and an inconsistency between the signal and the biofeedback modality. Interesting positive side effects were that some participants noticed an interplay of learning and fatigue effects, and that habituation supported their learning. The conclusion from study 1 is isometrically activated muscles are more difficult to control than movement-dependent isotonic contractions, and no difference in input performance was observed among the different body locations with isometric muscle contractions. The conclusion from study 2 is interactions with EMG-based systems in VR designed to register isometric muscle contractions can be improved with combined visual and tactile multi-modal biofeedback. We highlight the necessity of discrimination between isotonic muscle contractions and isometric muscle contractions. For further investigations, our apparatus can be found on GitHub. Thank you very much.